Thank you. Hey, good morning and welcome to today's webinar on advanced mobility. And thank you for joining. My name is Arupjyoti Bhuyan, and I'm in Idaho National Laboratories, where I'm the director of the INL's Wireless Security Institute and a directorate fellow in INL. First of all, I'd like to acknowledge the IEEE VTS, Vehicular Technology Society, for their sponsorship. And let me start with the talk today. If you cannot hear me, any difficulty at all, please drop a message in the chat. And before I start, just a logistics housekeeping item. I'll set some time aside at the end to answer your questions. So please put a chat in the chat box. Please post your questions as we proceed throughout the talk, and I'll address them, as many of them, in this meeting itself or offline with you. So here I'll describe the collaborative research in this hour between Idaho National Laboratory and North Carolina State University to create the scientific foundation for a secure 5G network that can be used nationwide for drone operations. So the NCSU team, research team was led by Professor Ismail Govens and Huawei Dai and Mihai Sisutu with their postdoc students and PhD students, which are all listed here. I'd like also to thank Dr. Nadisanka Rupa Singhi, who was involved at the very beginning of this research. So this slide summarizes the research work we did. And we'll go through all this, most of the points during this talk. Let's begin with the current cellular coverage that's available in US and most like the other countries as well. Looking at the fact that, and most of you probably know this already, that currently all the commercial cellular networks, they are designed and optimized for coverage on the road, right? For people, cars, and everything on the road, ground, not for coverage, RF coverage, which is the first thing, right? You have to have good RF coverage in where the drones operate, which is in the sky. So this research proposed and validated use of an additional set of antennas that will actually form beams. With this here, we use millimeter wave bands for all our work. In that, produce beams to cover the sky instead of the ground. And because of the beams, this separation it is easy to, or it is possible to separate quite well the coverage in the sky and the ground when you're using the same band. For example, in US, you know that 5G got started with the millimeter wave bands, 28 gigahertz and 39 gigahertz, right? So using that separation and reusing this same band, we can create coverage in the sky just as good or even better than the current coverage of cellular providers that we all use, right? So, and then if we particularly look at the drone operations, you can see that a coverage, not only just one drone, but a lot of times there'll be a swarm of drones, right? And then taking advantage of that, we can bring in some other technologies, such as the multiple access technologies, the non-orthogonal multiple access, NOMA, and the rate splitting multiplexes RSMA. So we can bring that to bear on drone operations and then connect with the same beam, which is used for one user, not just one drone, but a swarm of drones. Right? That will certainly improve the capacity even further. Now, here, let's see here, then we move on to look at how the trajectories can be designed to take advantage of the flexibility of movement of drones in the sky, which is much more, you know, that on the ground, roads and other things limit how much a person can move or a car can move to obtain optimal coverage, but drones can have the flexibility. So we could actually design the drone trajectory given the RF coverage in the cellular network to maximize the throughput, data throughput, and also the energy efficiency, which is really important, right? Because the drones operate with batteries and they have particular battery life. So before they have to come back to recharge them or some other drones replace them. So that's really important. Now, we also paid special attention, focus on security of the communications, which can be critical. So we bring in interference and then look at, superimpose that with RF coverage, and then design the trajectories for some cases that, some use cases that I'll go through. And next, of course, we can use the power of the signal processing to utilize physical layer security, not the app layer, but the physical layer itself, to maximize or optimize the secrecy capacity of those channels. And lastly, we can even introduce protected zones. As you know, on the ground, if there are some critical communication points, recipients, we could certainly build a barrier around it so that physically the eavesdropper, for example, cannot get close to the channel to eavesdrop and other things. So we can think of similar protection or creating protected zones, and how to create the optimal protected zone we'll also cover here. Okay, moving on to the next slide. So this slide shows a summary of how powerful we can, how powerful this 5G connection can be for drones, the secure 5G drone, compared to the other cellular connectivity, or just the traditional way of operating it with non-cellular coverage such as Wi-Fi, with, you know, directly with the hand. So of course, the first thing is that as soon as we move into cellular domain, then you of course have beyond line of sight coverage, right? Someone in the East Coast can operate a drone that's working that's connected to the same cellular network in the West Coast. So that's very powerful, of course. And then, of course, by adding the current LTE coverage, there have been experiments, actually flying drones with LTE cellular coverage. In INL also, we conducted some of those experiments. But the coverage here will be really not very reliable, right? And it will not be adequate because this coverage is coming from sector-wide transmissions that are now designed for the traditional operations, and that there'll be some leakage towards the sky and also from some reflections, but that's really not reliable coverage at all, where you can talk about nationwide coverage. So at a high capacity, right? So that is what is introduced by Secure 5G Drone. Then, of course, we talked about the designing and the trajectories such that we can take advantage of this radiation RF coverage, as well as minimize the threats or mitigate the threats, security threats. Now here, these two things, data rate and latency. As you know, the 5G is a transformational technology. The highest, the most critical transformation is actually the latency, right? So it can be at least 10 times less. It requires to be in the domain of even less than 1 millisecond for time critical applications, right? So we get that through that with the secure 5G drone, we get that, and also the ability to connect a large number of drones using the capability of the 5G massive machine type connection, right? Which is in the process of fueling the growth of IoTs, Internet of Devices, that are cellularly connected with 5G. So then we talked about the multiple access we can bring in technology for swarm of drones. That will certainly other increase in spectral efficiency. And then there are signal processing techniques that we talked about that can be applied for increasing the secrecy capacity and mitigate attacks then, right? So the last item is actually significant also. What 5G brings with security improvements. As you some know, that 5G actually, the 3GPP SA3 committee introduced significant advances or by looking in security. I'll just give you one example. In LTE, you have the subscriber identity is always transmitted at the beginning of the call, setting up the call. The IMSI is transmitted over the air in clear. So there, people have been snooping, taking out that IMSI and identifying a certain user and tracking them through that method. So in 5G, the IMSI is encrypted while sending it over the air. So you can intercept it, but it's not good because it is encrypted. There is another significant improvement, that is the integrity protection of the actual data flow. The signals have been always protected in LTE also, but the actual data, the integrity protection is for the first time introduced in 5G, and that can be, as you can imagine, would be really powerful, because if somebody changes the data during the transit, then that will really be detected, and that's really important. Okay, let's start with some of the details. Let's look at the first look at the actual RF propagation, how RF propagates in the air as opposed to be on the ground. And here it shows ray tracing for an outdoor environment for Rosslyn, Virginia. So you can see the buildings here and the 2D view here, and where's the base station. Now here we plot the fraction of the received SINR, which is good for connectivity, has enough SINR to have a meaningful connection. And we have two antennas here. One is the ground antenna that's down tilted by 10 degrees. And the other one is the antenna that we change for up tilt from 15 to 30 to 40, 45 degrees. And here it shows the results where you can see that if you look at the triangular ones, this set, they are considering distances up to 500 meters. And it shows the variation of the coverage as the height of the drone goes. And for this coverage, turns out that the 200 meter certainly is good. And out of those, the tilt at 30 degrees provides the maximum optimal coverage. But as you can see that if we, the 45 degree, it keeps on increasing, because of course it depends on the height, coverage at the height depends on how you tilt that upward antenna, right? So, and then the other set, these three that are dotted without the triangle, are when we're looking at not just up to 500 meters, but if you look at further out 1500 meters, it shows keeps on growing, right? So then the next plot shows how it varies as the distance for the drone increases from the base station. And that's what is depicted here. The ground one is, of course, we actually have the two beams here, right? The beam width also, of course, depends on determines the coverage. If they're sharper beams, they'll go further. And for both beams here, the ground coverage really dies out. At most, it goes up to 175 meter with the sharper one, and then 75 meter with the other beam. So whereas the ones that are in the air, they go at least about 2 times, right, as it shows. So that shows that, as we expect, because there is not many obstacles when you are operating at a height, aiming towards the sky, obviously we expect better. And this is just an example that proves that that understanding with some data. So given that they go further, now let's look at a actual drone trajectory. And what we are trying to determine here is, do we need to equip all the existing existing cellular towers that are providing the very good ground coverage at this point? Do you need to equip all of them with this additional set, or just some of them because the coverage in the air is far superior? For that, we pick this East Manhattan environment, where there's existing base station 1 and base station 2. And we look at 2. So this is the starting from the drone from here up to here. So we define 2 lanes, right, with waypoints. The first lane stays close to base station 1 and gets quite far away from base station 2, and then it comes somewhat closer. Where the second lane stays away from base station 1, quite close to base station 2, and goes to the destination. Now we start with a 4x4 array at the base station, right? So that's 16 element antenna array to form the beams. And if we do that, then we'll see that this shows the 2-dimensional view of the cover of the trajectory that the drone has to take to get to the destination. For lane 1, there is a unbroken, it can move itself, as you can see, the 3-dimensional view, move itself up and down based on the coverage or obstacle where it gets the best coverage. And it can complete the route, but there's not a continuous path in the lane 2. And at this point, we are just turning on base station 1, right? So, but as soon as we move to base station, the array of 8x8, which is more conventional 4mm wave beamforming, then you can see that even without base station 2 being equipped with that external coverage for the RF coverage, we actually can operate quite well in lane 2 also. So this is I think, important conclusion in the sense that if you look at the practicality, then it makes certainly simpler for different regions of the country how we can design where to equip the current base stations that are providing ground coverage to provide similar coverage in the sky. So let's move on to let's add then pedestrian safety here and that can be simply done by constructing a ground risk map and then superimposing it on the RF coverage. And in this case, let's just look at starting from close to the base station 1 to base station 2 so that it has good coverage throughout. Now, we just did this for 3 situations where the first one, we allowed only 1 turn, right? So, and you can see that it decided to go here, which it got away from the higher RF coverage. If we allow 2 turns, then it has more flexibility to actually stay close to the red and orange, right? Now, if you want introduce 1 more turn, then you can see there are some finer modifications where it can get better propagation. So this proves the principle that with more and more computation, it is really possible to tune the trajectory to avoid the paths that it should not be on top of from the ground and still get good coverage. Now, one more slide, one more situation here to explore, where we have multiple drones operating at the same time, right? So we are calling them lanes, or they're parts of the corridors where simultaneously different drones will take those different lanes. So here we show the results here for path lane 1, lane 2, and lane 3. And what it is showing is that if we use the optimal multi-agent pathfinding algorithm called conflict-based search, that'll take more computation. We get the solid line. But if we use a greedy approach where it just maximizes for lane 1 without regard for lane 2 and lane 3, then I think you can see that it gets fairly close. But for lane 2 and lane 3, the deviations will be much higher because they now don't have a choice when they are doing the greedy algorithm, for the trajectory is already taken up by the preceding lane. So that's, again, some interesting results to look at, where we can actually do this analysis for a real world situation when it is needed, when we go towards applying this. Now let's switch gear and look at the spectral efficiency improvement that can be obtained by utilizing the multiple access schemes. Right? So, and as it turns out, this actually brings quite a bit of resiliency improvement, and this is why. So we propose to use a swarm of drones instead of covering all the drones. We pick only 2 connections for the drone swarm, where there is one primary and one secondary. They are both active. And we position the primary and secondary drone. Of course, the primary for the most optimal RF reception, have the drones travel, the swarm travels. And then we can bring the which is actually going to transform some of the communication going forward for 5G, not only for drones, but platoons of vehicles, groups of medical devices. That communication is called device-to-device capability in 5G. And it's also popularly referred to as side link. It has been long looked at in LTE, it never took off. And in 5G, actually, it's the LTE standards are upgraded to 5G, not in release 16, but release 17. So we won't see those devices and capability in commercial equipment for quite a while. But that's the idea, that that's the concept here, that we can apply that to cover the whole set of swarms by having 2 connections within one beam to cover the entire entire swarm. So, and that introduces the concept of resiliency also, right? Active resiliency there. So if one gets disrupted or attacked, then the swarm can keep on operating using the other one. Now, we actually did some work to look at, compare NOMA and RSMA, and this plots the energy efficiency for the reception with for the second drone, this secondary drone in this case, as the height varies. And as you can see, this green line actually uses RSMA, and this is for the downlink. That's for the base station to the drone. That downlink is actually RSMA turns out to be superior to NOMA. Of course, when the height varies so that the secondary drone gets away from the primary drone, then you can imagine that that efficiency drops. But still, it's good to know that it's quite powerful to know that conclusion that RSMA, if I'm applying this, I'll pick RSMA for the downlink. And then NOMA turns out to be still good for the uplink, which actually for drones, the more communication can be, in the uplink. But downlink is important too for setting up the call and getting changes in the flight path or the mission and etc. So now let's look at optimizing data flow for using drones again in a use case that's quite important for emergency scenarios. So this could be disaster recovery, where the drone we want to connect to cellularly is actually cannot find a base station in that area because that area is affected and maybe the base station is knocked out, right, by, for example, natural disaster, a hurricane or something like that, earthquake. In that case, we can utilize the swarm of drones as relay drones, right? And that can connect the base station that's not close by directly to the target drone by acting as a relay. And not only that, optimize those positioning of the drones where it can have optimal connection as well as mitigate interferences from sources on the ground. So you can see that we applied the graph theory, and what we do here is that we can see that we did that for two drones, the recipient drone being first in the not that far from the ground, 25 meters, but the second one is up at 200 meters, quite far above the ground. So in this case, then you can see the results here, that the drones oriented themselves, the relay drones, so that it can not only avoid the interference where there are 7 interfering nodes, and there are actually 8 drones here that providing the relay functionality. So in either case, they position themselves to provide the optimal coverage and secure coverage to the intended drone. This other plot here shows that the data flow, right? The maximum data flow, of course, depends also as we vary the drone height. As you can see here, in this case, it shows maximum to be 200. And these plots are as you raise the threshold of how much you have to, or reduce the threshold of how much you have to receive to communicate, then of course, as the threshold gets lower, it gets more throughput. But the important thing is that there is, again, just like other trajectories, they are for particular heights, this will have better coverage than the other heights. Now, let's do one more thing here. I think 2 more slides on interference, and I think we're about the half an hour mark, so it should be okay with the rest. So here what we do is we actually make the interference not only come from the ground, but also from the sky. And this can be easily done, right? The attackers can fly other drones to interfere with this. And in this case, we have also a multiple flow problem here, because we are looking at 2 drones here, UE1 and UE2, and 2 base stations, and we are using the same relay network to establish connection between these UEs and the base stations, whichever is the best connection. And we are using a relay network of 12 drones and 4 smart interferers that are positioned here now. Now, the results are, as you can see, that again, those relay drones position themselves. Of course, there are some close to the UE and some close to the base station, so that it can bridge the gap from the connection to the base stations to the UEs. And the last one on trajectories is specifically looking at the maximizing the life of the battery on the drone, right? and looking at only, of course, the RF energy spent, not the to fly the drone actually, which is the mechanical. So for wireless transmission, what we have looked at here is this use case actually is another important one, which is a set of drones, the green ones, is collecting data, sensor data from the ground, and relaying it through a relay network of drones to a base station that not directly reachable by the collector drones. Now, if you look at this plot, the flat line shows where we put the drones at fixed location. I believe it's 35 meter up, and they don't move. And all of them are at fixed position. Then, of course, the here in this case, it's showing 300 seconds, which is will be 50 minutes, right? About an hour. But when we allow the drones and also the relays to move around freely, and here you can see the interference is coming from the ground. These are the channel heads that the green drones are collecting to be relayed back to the base station that's not directly reachable. And you can see that when we allow all the freedom for movements of the drones to position themselves, reposition themselves, then the lifetime can go up by quite far as two times, right? And of course, that's it's quite important to operate drones for longer time. So that is the I think that we can then let's look at other technology called enhanced intercell interference coordination that has been introduced by 3GPP and already there from LTE days. What we have noticed is then that this again, there are two base stations, right? This is the cellular base stations we talk about, and both are equipped with the upward set of antennas also, which they can cover the drones. And this drone actually is the, as you know, the cellular as the device, the 5G device, in this case, this drone connects to a cellular network. It camps on the strongest signal to noise ratio, right? So although it can listen to other drones, other cells close by, and that's how, you know, it is the handover is triggered when it moves from coverage of one cellular tower to another cellular tower. But what we notice is that in this case, this base station being the primary coverage is the actual connection. We noticed that there could be significant, sometimes reflection of beams from the ground that can cover areas far longer than it will cover normally, right? So, and the signal strength may not be much, but they can be still significant. So, and that can be mitigated by this technology called the intercell interference coordination. The basic idea is this. So imagine this down tilt is coming from this base station on the left, and the actual up tilt communication for drone is coming from the base station on the right. And this idea is that you have some coordination between them so that you have some of the subframes you blank out from this base station on the left. So in that case, there is no interference. Wherever it is emitting, covering, doing beam transmission for the ground coverage with information, then that will be conflicting. And this actual conflict depends on a lot of things, right? How primarily what strength that reflected signal is, but still good to have that improvement. This will take away from ground coverage, but again, depending on the particular use case, depending on the location, it is possible that what you are communicating with drone for a certain period of time could be much more significant than the ground coverage, and for those periods of time, we can certainly apply that coordination. Here are some results, simulation results. The leftmost, okay, here it shows the received signal to interference ratio, and here it shows how the strength is. Of course, the further higher up is, and the further right is much better. So the black line shows the condition where you actually do not have any coordination, right? And there is no up tilt antenna. So this is pretty poor, but as you move to the furthest right, that's the best one that has the up tilt covering this, and then for the down tilt from the other one, then you're coordinating that, and you can see that the really large improvement that can be obtained. So that's really good technology to have when we need it. So the next, I'm going to talk about the protected zone, and these are physically protected zone. So what I mean is this, and this shows the projection on the ground. Of course, the transmissions are towards the sky, and the drones are at particular heights. But you can imagine that on the ground, just like we talked about in protected zone, you can create a barrier so that nobody can get inside that barrier, and that's the protected zone within which critical communication is coming to intended recipients. So here, if we look at the drone, this blue region as where it needs to operate without with high security, then we can design protected zone, and here we saw 2 protected zones which we analyze what zone would be the best. And this can be achieved. Think about in the case of swarms, you can use, as we said, we actually target 2 active primary and secondary drones for connection to the drone swarm. You can take the other drones and place them and form a boundary which a attacking drone cannot come close, cannot encroach, right? So that's our protected zone, just conceptually. So here we look at the design, say we can create cover a certain area. So what that area should be, and the extreme, the protected zone 1 shows that the width of the area is small, but it goes far, right? Whereas the other protected zone is we widen the coverage of the protected zone beyond the user zone on the width, but then it reduces in distance. So those are, of course, the extremes. The idea here is to prove the principle that can be designed, and that can be quite important how to design it. So these plots here, we are looking at for 2 different heights, right? When the drone is about placed at 10-meter height, and then when the drone is placed at 100-meter, you can see that this varies with the width or how wide that zone is. You can see that for the one that's much higher, the sharp protected zone is much better. So the angular width is smaller, however, the distance is much larger. Whereas on the other extreme, for the drone at 10-meter, where it is the secrecy rate, that's what we're looking at, is best is when it is a much wider protected zone, but again, it will be coverage will be much less. So this shows again, as I said, depending on the height of the drone that is being covered, it's quite dynamic. It can change, and then but it is a useful tool to have when we need it to create that protected zone within a swarm of drones. So I'm getting towards the end here, so I do want to leave some time for any questions and answers. So next 5 minutes or so, let me end up by looking first at the publications of the research work. So far, 31 papers, both conferences and journals. Most of these are IEEE ones, including IEEE transactions. And there's also a book chapter. And we did a summary paper once a year. This research was done over 3 years. And every year we did a summary, starting with 2091 in the PTC conference. Then in the next two, we did it with the IEEE Aerospace conference. So you can find these papers easily. And then these actually have references to all of the details in those papers. Now, details of this paper, so you can find those references, or you can always drop me a note in my email. I'll post it towards the end when we're addressing any questions. So that we also file a patent for the novel proofs of principles that can be applied in real world situation. And that patent is also mentioned here. Now, this is, let's end this talk with, again, going back and kind of summarizing what we covered today, what are the key points. And I bring back the slide that we showed first, showing the advantages. And just to refresh your memory, this is the summary. So first of all, RF coverage. If you want to connect a device with RF coverage with wireless connection, then of course, first thing first is you have to have reliable RF coverage where you want to connect that device. And with traditional non-wireless, non-cellular, of course, that have to be line of sight. And then as you move to cellular, then you get beyond line of sight operations. Then what we do not have in LTE, because the current networks are optimized, even including 5G coverage, right? At this point, are optimized for ground coverage. So there is not really reliable RF coverage in the sky for drones. So by introducing the additional set and reusing the same frequency band, so that these license bands are not, cellular operators cannot have the luxury of using same part of the license band taken away from ground coverage. So using the same band that they have already purchased, they can mirror the ground coverage in the sky for really high capacity, high reliable RF coverage or cellular connectivity, which can be the future. Now, we talked about how we took advantage of drones and movement of drones to optimize and take advantage of really the beam-based transmission, not the normal sub 6 gigahertz, as you know. Mostly it is the sector communication, right? Whatever you put out in a sector that covers 120 degrees, all of the conversations go into the same transmission. Whereas in the beam, you can, for each user, you have a single beam to cover that. And we saw how we take advantage of that for beam-based transmissions to further increase the spectral efficiency, as well as introduce resiliency for drone connection. As I mentioned, data rates, of course, with the millimeter wave bands, you have far wider data bands available compared to, say, 20 megahertz license of LTE. You got 200 megahertz, 10 times, right? So obviously your data rate would go up somewhat like 10 times. Latency, that's new, completely brand new in 5G. The ability to connect to ability, and that mostly comes from the new radio itself, which has been really re-architected, redesigned, and is very powerful. It's very frequency as all. And with that, you can actually, the carrier frequency itself in the OFDM technology, the carrier itself can vary from 15 to 30 to 60 to 120 to 240 kilohertz. Whereas in LTE, it's either fixed at, I think, 15 kilohertz, right? So as you increase the band there, the carrier frequency with a bigger band, then you can have much frequent repetition of the RF frames. And in addition, they've introduced also what they call subframe, whereas within the frame, you can have new data inserted in subframe. So all of that if you look under the hood, you'll see that the new radio brings a lot of that latency improvements, and some, of course, will come from having that in the edge network itself, what mobile edge computing, which is another technology, right? That's available before even 5G, but in conjunction with 5G, those can reduce latency quite a bit. Now, and again, we talked about the powerful techniques in signal processing, right? That you can design, security aware beamforming. You can introduce artificial noise. You can do pre-coding. All of those signal processing techniques can be brought in this case with secure 5G drone as well. And we did not cover too much of it in today's talk because of the time allowed. But if you look at all the papers published, then you'll see a few papers on that subject also. And then lastly, I mean, so there is certainly we can not only make this secure 5G drone reliable and resilient and high capacity. At the same time, we can make it highly secure. And that security will be further enhanced by 5G, which is the best or the most secure cellular network. Of course, it's the latest one. So we'll see whether that can be further improved as we have 5G rolled out or more widely used. And as you know, LTE, actually some of the security problems were surfaced after LTE was in the field for 10 years. You can still see research papers looking at LTE security issues. The point is that with 5G, security is quite well covered. And in that case, we can take advantage all of the secure new security procedures, including the encryption of the subscriber identity IMSI over the air, and also the making sure that the data communication itself is not messed with. So the integrity protection, we can take advantage of that for data that's new in 5G. And of course, as we learn more and move towards 6G or the next Z or the future Z, where you call it, then that can be propagated, right? So if we have this additional RF, additional set of antennas transmitting beams for coverage in the sky. So that, I believe, is the last one. Thank you again for attending, for coming and listening to this. And let me now put back, let's see here. Let me put it back on the first one where you can see my email, and let me drop my email address here on the chat. Okay, and in the meantime, if you have any questions, you can either drop it, or you can even, I think if you're able to, you can also ask. So that's my email, inl.gov. All right, right here. Okay, I'll wait for the last few minutes then for any questions you may have. Okay, Sihan Tung, you raise your hand.
Yes. Yes,
Yes,
thank you very much. I have a very quick question. I mean, this is a very nice idea, and I'm also interested in the security of the drones because we cannot operate without any security. Unfortunately, I haven't seen many studies that focus on the security of the drones.
right,
That's one major problem. And by security, we can have physical attacks, we can have cyber attacks as well.
right.
So that is something that I'm really interested in working. This way we can make sure that the operations, not only for um, network, but also the whole drone operations can be secured. Another concern I have is that the battery life of the drones is extremely limited, right?
Yes,
Um,
yes.
I mean, it sort of depends, but commercial drones can go up to, let's say, maybe 40 minutes.
Mhm.
So, which also means that if we want the drone to return back to us, we only have 20 minutes of flying range,
Right,
flight time, right?
right.
And that is a major problem in my eyes as well. So, also, if we are going to do anything additional on the drone, like creating a Wi-Fi hotpoint or any 5G or whatsoever, then that will be another concern we need to worry. Do you have any ideas about these problems?
Yeah, and first of all, those are really, really relevant concerns or so areas to look at and do research. So the first one is security, and you're absolutely right. I mean, people, and in general, security always comes last, right? So, but hopefully we have just started looking into it. And as you can email me if you don't find the papers. But I think, or I can provide references to them directly so you can find them. But we have actually, as I said, we have for large part, we did look at security and again, covered not everything, right? But just the initial probably work or, using, of course, other existing work as well. But certainly take a look at the maybe the summary papers at least, where I think one area I did not get to cover very well here is the signal processing techniques, right? The beamforming and even doing artificial noise and things like that, which are some of them are well-known techniques that can be applied here for security of the transmission itself. But when you go into physical security and stuff like that, that's why particularly we looked at I mean, for a swarm of drones, maybe you have to create a swarm just to have that security around, right? Physical kind of boundary around. So there are some ideas like that, but I'm sure
Mhm.
there will be a lot more that will be needed if we go to in 3-5 years. We really go to a situation where this drone are that corridor is widely used, right? So and that's the
Yeah.
whole idea of this. Let me look at the second point at the battery life. I mean, that's really you're right on. I mean, what I do see that when we do move into a large use of drones in the sky, so 400 meters high or up to a certain amount, which I still FCC and I saw they're doing a lot of work, right, where we have this under the umbrella of UTM, the UAS or drone traffic management. Uh, so there, I mean, I do think that there'll be stations along the way, just like your electric car that you have to charge, right, as you go along. And
Mhm.
not only that, but for you can think about, say, in the agricultural big area where the drones are doing things, going out and looking at seeding and fertilizing and doing all kinds of things, right? That people are thinking about already, or some of them are doing also. There'll be at certain time there'll be like you said, 40 minutes, right? Say in 20 minutes, other drone will go there, right? And you place the drone that with an upgrade to come back. So there'll be a lot of schemes like that. But this is the starting. So this is very exciting. I mean, if you are able to work in that area, either security or battery life, I think that'll be really, really promising for upcoming technologies.
Great to hear. Thank you.
Okay,
Thank you.
you're so welcome. Okay. Any more questions?